All right, so this is my project 2. So we were tasked with designing an optimal thrust profile for a hobbyist rocket to maximize its altitude. And then we were given all the equations and variables we'd need, and then all the initial conditions and given data, and then all of our tasks here. So if we go to my code, we can start with the constraints and stuff. So I wrote all that down: gravity, drag coefficient, air density, cross-sectional area, specific impulse, the thrust, the initial mass, and the dry mass. And then we moved on to the thrust control strategy. So the first one is constant max thrust until the fuel runs out, just using a simple at function equal to or times Tmax. And then I moved on to the strategy 2, which is the linearly decreasing thrust from Tmax to 0 over a burn duration. So I did that by making my burn time, subtracting my masses together, times the initial specific impulse, times the gravity, and then divided that all by the max thrust. And then put that into another at function, multiplied the matrix by Tmax times max of everything divided by the burn time. And then I used this here to solve using both strategies. I extracted my state variables of height 1, height 2, velocity 1, and mass 1, and then computed the results here with these functions, and then plotted everything here. Made a subplots so that way it all would plot on the same one. And then here I used this function to simulate the thrust, using why not the time span, using options ODE set, and then ODE 45. Made my ODE system here with this function dy dt, h, v, and m, and then use this as to stop the integration to, tell me when the velocity becomes 0, which is when flight becomes 0. So if we come back and we run this, it should pop up, yep, these 3 graphs. And then I'll also tell you, if I move this out of the way, 1 second. It'll tell you here the strategy 1 max thrust and max altitude and time to max altitude. And then strategy 2, the max altitude and the time to max altitude. So I then have all of my, data here. And then these 3 graphs I use to kind of compare the results. So mass over time with strategy 2 is obviously a lot more exponentially looking because the fuel depletion is a lot slower. The velocity over time, strategy 1 is obviously going to be a lot faster because you're just dumping that fuel out. You're not really controlling how fast the fuel is going because you're just max acceleration trying to get up there. So you get a lot faster and a lot over that period of time compared to the linearly decreasing strategy. And then the altitude is much different. The altitude given strategy 1, you end up getting a lot higher, but you run out of fuel a lot faster. So given these 2 things, if we go back to the problem statement, we do determine that the mass of the system never decreases below the dry mass. And then I also found the max altitude reached as shown here for both. The max altitude here is 890.73 meters, and the max altitude for strategy 2 is 394.63 meters. And then using the graphs, you can see the mass over time never goes into 0, which would determine that it, or never goes below 0, which would determine that it is lower than the initial mass, or the dry mass. And then if we go back to the problem statement, and then I tested both of these, so that is my code.